Just for fun, to start this one out, I was recently browsing or came across the uh, exam report, the grade distribution report for last year, Math Methods. Let's see how that went. So, graded assessment one, this is the coursework. So, the stuff that you guys are currently doing in your school. Um, the mean was 62.6 out of a total of 100. So the average grade across all assessments was 62.6%. Standard deviation 19.8. So we've been recently doing some statistics stuff. Standard deviation basically just means that 19.8 either side of 62.6, you're going to look at like roughly 68% of people that do methods are going to fall between, what would that actually be? Let's have a look. 62.6 minus 19.8. So the lower bound of that was 42.8. And then we do plus, the upper bound of that is 82.4. So about 68% of results fell between 42.8 and 82.4% as an average grade, which is honestly higher than I was expecting. I mean, of 62.6 for the coursework. That's obviously not necessarily VCAR moderated, so do with that what you will. Your school will have their own internal statistics on where the class averages are at. There'll be a better benchmark for you to have as to how you're currently performing. Okay, exam one. So this is the thing you do start of November, basically. Tech 3. Mean mark was 37.1 out of a total of 80 possible marks. So that's this little calculation I did before, which means the average grade was 46% or so. And so basically what that means is if you get 46, well, if you got 46% on your exam one, you would have gotten, I think it ends up being the case that you would have gotten a 30. I think they set the mean, whatever the mean is a study score of 30 for that. And then, yeah, standard deviation of that was also very similar, 19.3. So, although to be fair, this one's in terms of marks, so 19.3 additional marks when the total is 80 is actually a bigger standard deviation than the 19.8 when it was in terms of percent. Because this one's out of 80 rather than out of 100. So that 19.8 counts for more. So essentially what we're seeing is there is a wider distribution of grades in exam one versus the coursework. And it's not super noticeable. That's why we do have those statistics. So if you see here, this is the coursework distribution. You can see the average is like smack bang at a C+ level. If you take note of how wide that distribution is, you can go down and you can notice, yeah, I mean, it's not really super noticeable there. Ungraded and below E, very rare. Whereas over here, there's a lot more skew to the left of the mean, and this mean is sitting at a D. Oh, sorry, that's a B. Yeah, I can't really see it from there. So the mean being a B versus the mean being a C+, you see a slight difference there. Then the last statistic, exam 2. This one's out of a total of 160 marks, and the mean was 81.6 marks. So that's this statistic there, basically saying that the average grade was 50%. So if you got 50% on your exam 2 and whatever it was, 46% on your exam 1, you were pretty much smack bang at a 30 study score. So when you guys start looking at your at doing actual exam revision, if you do them under time conditions, these are the kinds of things you can look at to sort of benchmark yourself against the rest of the cohort. These are available, publicly available, VCAR reports. You'll just do VCAR grade distribution 2020, 2020 whatever, and you can look at the report for that particular year. So when you're doing that exam, that past exam, under test conditions specifically, make sure you do it under test conditions. When you do that, you'll be able to benchmark yourself against the other people who did it at that particular year. And so in that way, you can say, oh, look, the average was this, I got this. Is that good? Is that bad? Well, that's up to you to decide what you're particularly aiming at. But yeah, so average is 50 there. This is what the distribution looked like. Looks very similar to this distribution here, although this one was centered at a B, and this one is centered at also a B. Yeah, okay, so it's the same sort of stuff. Yeah, standard deviation is probably going to look different. Yeah, standard deviation of 35 versus standard deviation of 19.3. That's less of a difference than you think, because if the first one was out of 80 and the second one was out of 160, it basically means, okay, so if I do 35 divided by 2, I'm going to get pretty damn close to, yeah, okay, 17.5 as opposed to 19.3. So the standard deviations are very, very similar. When you weight it against the actual number of available marks versus marks actually achieved. So that's why they had a very similar skew to the distribution. Yeah, no, interesting statistics. There's only around 15,000 people that are doing methods, which is surprising to me. There's not actually all that many of you. I guess that makes it also a little bit more competitive as well. When there's less people, well, does it make it more or less competitive? It depends on the quality of person, I suppose. Because a lot of people are in general doesn't necessarily mean general's not competitive or competitive. Anyway, that's just a little thing I thought was worth bringing up for the recording of this class. Onto the actual agenda for today, which is to basically have a look at the functions and relations, like application style question stuff, essentially. And so there isn't really a whole lot to be talked about as far as lecture goes. There are a few key examples that this chapter in particular is going to look at. Namely, we're going to look at how we can use linear models to describe a particular scenario. We're going to look at how we can use piecewise, again, to describe a scenario. And, well, in this example, we're looking at how we can use quadratics to describe a particular scenario. So let's dive in. Example so-called 24. We have a book club with membership fees, essentially. My preferred approach in pretty much every single scenario when it comes to answering a question is just go straight to the actual end of the question. What are we actually trying to achieve? None of this matters right now if I don't actually know what the target is. And in this case, the thing that we're told to do is construct a cost function, right? We'll figure out what all this is all about later, but fundamentally this is going to orient our aim. That's step one. Figure out what are we actually aiming for in this particular scenario. We want a cost function, which means cost is going to be on our y-axis, the cost of whatever this thing is, and on the x-axis will be determined by the background information. Okay, now let's read the background information. Book club, membership fees, and books purchased. So we have some sort of fixed fee and we have some incremental fee. Very, very common when it comes to linear. If you have a fixed one-off thing, and if you have paired that with an incremental thing, notice it says each book, that makes it incremental. That's going to be a linear equation that describes that particular scenario. In this case, we're looking for a cost function, and it's going to be used to determine the cost of different numbers of books. So that key sentence there is essentially telling us that the x-axis is going to be in terms of the number of books that are associated with it. So, the way it works. The fixed fee is going to be, or the fixed amount in any scenario, is going to be your plus c value. If you think about having your y equals mx plus c for any linear, which I'll pull up in a sec. There we go. Think about having your y equals mx plus c. Then your plus c value is going to be whatever that fixed amount is. That'll focus eventually. And so in this case, we have a fixed amount of $60, which is why we're now going to have y equals mx plus, what did I say, 60. We have that $60 fixed fee. Then we're told that each book purchased is $10. And so if our x-axis is representing the number of books, then that means that this variable x is representing the number of books. And so if we think about how we would construct this coefficient of m is a multiplier on the number of books. That's what it literally does. M multiplied by x. So if x is number of books, m is a multiplier on x. What are we trying to multiply it by? Well, the cost of the books, which in this case is $10 each. So we now have y equals, almost wrote m again, y equals 10x plus 60. Now you can rewrite this kind of like how the book has done with using c instead of y, so you can write it as cost, and then you can use n for number of books if you want, but fundamentally it's the exact same thing. C of n equals 10n plus 60. You can even use dollar signs if you really want. And then yeah, when it comes to actually sketching this, it's just sketching a linear. So if you look back at the screen share with the actual book itself, you'll notice there is a series of dots which has a y-intercept of 60, makes sense for linear, and it will continue on and on and on, and typically until infinity, but, well, we have to cut it off at some point. Now, the reason why it's made up of a bunch of dots is because when it comes to things that have discrete specific quantities, for example, you can't have a fractional number of books. There is no such thing as half a book, or an irrational number of books. Then what you have to make sure you don't do is draw a straight line that connects everything together like a full linear, because only the natural numbers are valid in this case, or more specifically the natural numbers including 0, because natural number set does not necessarily include 0. We can't go to negatives because, once again, negative numbers doesn't really make sense for the number of books that are available to us. And so that's pretty much it. When you have a fixed amount and an incremental amount in whatever the scenario is, it's going to be linear. You go to the action statement that's in the actual question to figure out what are we trying to achieve, and then you use the background information to figure out what's going on. Okay, next up, action statement. Sketch a graph of the cost function. Cool. Once again, we're doing cost. This is where we're going to use our background information, figure out what's going on. In this case, it's particular rates for sending letters, and it's contrasting that against the mass of the letter with the price of sending that letter. So up to 50 grams is going to be a 70-cent cost. Anything between 50 and 100 is going to be $1.15, so on and so forth. These are fixed amounts for a variable amount of m, right? So up to 50 grams means anything from 0 to 50 is going to have a fixed amount of spend of 70 cents. So if I send a 37-gram letter, it's going to cost me 70 cents. If I send a 49-gram letter, it's also going to cost me 70 cents. It's a fixed amount. And we have that for different domains. Now, we're told it's a cost function, so cost, this column, has to go on the y-axis. Whatever the function is describing goes on the y-axis. whatever goes on the x-axis will be the thing that it's contrasted against. In this case, the question doesn't really say in the action statement what the domain or what the x values are going to be associated with, but this table is what gives us that information, because our y values, our costs, are associated with masses. And so what that means is we're going to, it implies that mass is going to be on the x-axis. And so that's what we do. You'll notice these are depicted by basically a piecewise function. So essentially, whenever you have a set of different domains, you basically have a piecewise function, where each of them is going to have a separate segment that's going to be valid over a particular domain. So for instance, this one here, that's going to be that 70-cent one. You can see it's somewhere between $1 and 50 cents, and it goes from 0 to 50 on the x-axis, which is representative of being between 0 and 50 grams. The reason it's a flat line is because cost, y-axis, the y value does not change for any mass between 0 and 50. Now, it says up to 50 grams. For a bit of tighter wording, it probably should say up to and including 50 grams, but even if it didn't, you would use the next statement to figure out whether you draw a dark circle to include it or whether you draw a open circle to exclude it. That's what this statement says here, over 50 grams. There's no ambiguity there. It has to be over 50 grams, not inclusive, which is why the over 50 gram up to 100 is going to be a white circle start at 50 and a dark circle end for the inclusive. The white circle must therefore leave a dark circle behind in the previous section, and you're not going to draw anything that connects these two things together, because that would imply that there is a certain, or that would imply that the mass of 50 could range anywhere from 70 cents to whatever this one was, $1.15. You want to leave these as blank, discrete values. And so yeah, basically you're just going to draw a horizontal line at each of these y values, and each of the starting points is going to be an open circle because they always start with the sentence over, and they end it with up to. That's pretty much it. So that's the first part of the action statement, sketch a graph of the cost function. Next part, give domain and range. Okay, well that's pretty chill. Domain and range, well, domain is literally given to us, right? That's just all the possible x values in the scenario. Now, these white circles, you can't let that think you exclude 50 or exclude 100 because there is an accompanying dark circle along with it. So as long as there's at least something along a vertical line where it's defined, that part is defined in the domain. So everything up until 500 is going to be inclusive. Now, what is interesting is they started this one with a white circle, with an open circle, even though all they said was up to 50 grams. Now, the reason it's a white circle to start there is simply because that means a 0 gram letter. And if your letter weighs 0 grams, you're not actually sending anything. And so for that reason, it'll be excluded. You do have to have a certain amount of common sense when it comes to actually thinking about the scenario and what is realistically plausible in that particular scenario. Which is why domain is going to be from 0 to 500, where the 0 is a non-inclusive, using that rounded bracket, whereas 500, inclusive, using a square bracket. Yeah, so that's domain, and then range. Cool. So range is all the possible y values in the scenario. Once again, that's going to be this cost C here. Now, again, as I said, there's no lines that connect any of these individual values together, so we're going to use these curly braces to represent the range. Right? It's going to be all the possible y values in the scenario. The reason why we use curly braces is because curly braces imply that every single thing in the braces separated by commas is an individual element of the set. Or in other words, each of those are specific values. It doesn't imply anything between them. like this doesn't imply everything between 70 cents and $1.15. It means specifically 70 cents or $1.15, nothing in between. That's domain, that's range, and the rules that define it. Okay, so this is one where a lot of people get caught up. It's not really taught particularly well in most schools about how you draw a horizontal line or how you describe the equation of a horizontal line. I guess it's just sort of overlooked because it's not actually really that hard, because all you do is you just look at the y value of the horizontal line, and then your equation just is that value. It is the graph of y equals 70 cents or y equals $1.15, because it means that it doesn't matter what x is, y is a constant value, or in this case, cost is a constant value. So that's why there's going to be a whole bunch of these, right? The 70 cent, the $1.15, the $1.70, the $3. They're all going to come from here. I said at the beginning, when you have multiple domains, you have a piecewise. And the rule of thumb, I would say, is whether you have a graph like this, whether you have a table like this, the point is, if you can identify clear jumps between the lines that you're drawing, the best way to describe that thing is a piecewise function. That's why we're going to use a piecewise for this. And so all you have to do after that is write the equivalent or the respective domains for each. So it works completely horizontally. So the 70 cent one is going to be from 0 to 50. Remember, use your correct inequalities here. 50 to 100 is this one. This one, whoops. This one is 100 to 250. That's there. 250. 500. And then, yeah, those are deliverables. So sketched, that's this right-hand side. Domain, that's this. Range, that's this. Rules, that's this. Okay, next up, action statement. Construct a function that will give the area of the enclosure. Cool. So whatever this scenario is talking about, we want to get an area equation. Cool. We have a householder. Huh. I don't think I've ever actually appreciated that word before. I don't actually know what that means. A householder has 6 laying hens. I guess it's got something to do. Maybe it's terminology for people who have hens. Unless they mean like a homeowner. Anyway. Point being, they're going to construct a rectangular enclosure to provide a maximum area for the hens. All right, so we want to create this rectangle that is going to be the enclosure, and we want to maximize the area of that particular thing. We're told we get 12 meters of fencing wire, and well, yeah, that's everything before this statement. Cool. So we know we want to deal with a rectangle, so the first thing we should probably draw is the rectangle, and that's what they've done in the book there, although to be fair, they have filled out a fair bit of that already, so it'll be better if we see it develop live. So the way I would start this one out, if all I had was a text, start by drawing a rectangle. We know that we want this to be a rectangular area, and so that's what we shall do. Next up, the other key piece of information that we have is that it is created using 12 meters of fencing wire. So basically, all of these sides have to add up to 12. The perimeter of this shape is 12 because the perimeter is fence. So if we know our total perimeter is 12, then all we've got to do is start labeling our rectangle. It's going to have 2 lengths, 2 widths, and the sum of all of them has to be 12. So 2L plus 2W is going to equal 12. Okay, that's one equation we can create, but that's not the equation that we want necessarily. We want an area equation. What is the area equation of a rectangle? Well, it's just length by width. There's a slight problem with this one though, and that's that when we create our equations, in order to graph them, we need them purely based in terms of one variable. Anything more, and we can't really graph it. Or you can, but it's really not a math methods thing at that point. And so what we're essentially trying to do here is figure out how can we get this to only have one variable. And the answer is substitution. So it doesn't actually matter if you keep it with L or you keep it with W. All you got to do is pick one of them and then get everything in terms of that one variable. And that's what this second equation was all about. You can see that we have two separate unique equations that have both L and W in them. When you have that, you can basically achieve whatever you want. You can get it in terms of L, you can get it in terms of W, up to you. So in this case, we're going to divide everything by 2. L plus W equals 6, and then pick your poison. W equals 6 minus L. And so what that means is every single W is the same thing as 6 minus L. So we come back to here with our area equation. Instead of saying area is equal to length times width, the width is now 6 minus L. So finally, we have 6L minus L squared. We have everything purely in terms of one letter, L. So that's step one of the process done. We've constructed a cost function. Oh, sorry, not a cost function, an area function. It says to call it A. Yep, we called it A. Nice and easy. Oh, this one did actually say to get it in terms of length. That's what I get for not reading ahead. But yeah, fair enough. Lucky us, we picked the right one. Next up, sketch the graph. Cool. So, sketching a quadratic, pretty chill. You're better off using this version of the quadratic, much easier to work with. The reason why is because the factorized form of the quadratic is basically a null factor law. It tells you where the x-axis intercepts are going to be. So if you imagine replacing the a with 0, it basically means that either L equals 0, so that's going to be the first cut, or L equals 6, because 6 minus 6 equals 0. That's going to be this one there. Then from there, to draw the rest of the quadratic, you need to know whether it is a negative quadratic or a positive quadratic. In this case, well, in all cases, you want to look at the sign of the L squared, or the squared term, which in this case is an L squared. Since negative, it's going to look downwards, like this. And thus, we've created our quadratic. It's not going to go further than that, because... do I say this now? Yeah, sure. So reminder that this is an area equation, and on the x-axis is length. For area to exist in the real world, has to be positive. So any time we go below this x-axis, we're looking at negative a values. So that's not good. Yeah, that's probably the most succinct way I can put that. Okay. Now we got our graph. We may or may not need the y-intercept. Let's find out. Oh, sorry, the turning point. Got a graph. Find the maximum area that can be fenced. Ah, yes, so we will need it, which is pretty common. So, maximum area. This is an area equation. And so if area is on the y-axis, then the maximum area is going to be the biggest y value. So how tall does this get up the y-axis? So taller, 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 taller. There it is, turning point. So we need to find the y value of this turning point. Not the x, not this thing, but the y value, because the y value is area. That is maximized area. But in order to find that, we do actually need the x value, or in this case the L value, to actually accommodate for that. A couple of ways you could do this. You could use this version of the area equation and then do the axis of symmetry equation. So that'd be like your x equals negative b on 2a sort of scenario. That works. Or, my preferred approach, if you have x-axis intercepts, it's just the midpoint. It's always the midpoint. Now, worth pointing out, only always the midpoint for quadratics. For cubics or anything else, yeah, For anything else, use other methods like the derivative, or depending on where you're at, you may have to use a CAS. So midpoint between 0 and 6 is 3. So we write 3. That tells us that for a length of 3, we will maximize area. So what do we do with that? Well, this is where we go back to our actual area equation. Whichever one you want to use, doesn't really matter. If I sub in L equals 3, I should get the maximum possible A. So that's what we'll do. Here makes most sense to me. So we're going to have, what did I say? I say A equals 3 bracket 6 minus 3. And then, well, we continue from there. A equals 3 times 3. A equals 9. So that's pretty good. That's going to give us our maximum area. Now, when it comes to application scenarios, always worth paying attention. Do we need a unit for a particular answer? We didn't really have to have a look at any of that before because we just had to sketch graphs and describe graphs. We didn't have to actually answer any particular things about it. In this case, we did. And so we now have to look at the unit that was associated with this stuff. And in this case, our lengths are in terms of meters. So when everything we've used is in terms of meters, we're now going to do our area in terms of meters squared. That is required. You won't get the mark if you don't put the unit. At least if your school's doing the right thing, they won't give you the mark. That's pretty much it. So if we had to do a similar thing for the other scenarios, we would be giving it in terms of dollars. Like, for example, if I said, what is the cost of a 350 gram parcel or a letter, you would have to look at the 350 gram section on the graph and then look at the Y value associated with that, which in this case is $3, and so you would specifically write $3.00. I would even go out of my way to say 3.00 rather than just 3, because that's the number that was given in the book. Like, that's pretty much all there is to that. You should get this, like, you'll get the same mark either way, but if we're talking about how you can make your answer look as favorable as possible, then it's always ideal to use exactly what the book is giving you, or what the question is giving you, rather. So that's that one there. And then, what could we say about this? Yeah, it'll be basically the same thing. Like, what is the cost of 7 books? Or at least what would the overall fees be in a particular year if 7 books were purchased? So you would include your membership fee of $60 and then do 7 times 10. That's how most people would do it. In methods, of course, we now have equations that describe that. All you're doing is subbing an n equals 7 in there. That's not actually depicted on the graph, so you can't just read it off. Although, to be fair, I don't think you can read any of these off of the graph unless you're really good at estimating. But yeah, that's pretty much it there. This is chapter 5H. It'll do a lot of those sorts of things. So you'll see you've got a fixed amount and a variable amount. That's going to be linear. Again, they've kind of reused a postage example, so you can kind of immediately tell it's going to be the piecewise. And it's the same thing, right? $1.20 up to 20 grams. $2 for over 20 grams. So, same sort of thing. In fact, this is exactly the same thing. This one here, a bit more nuanced, but still not too much different. You've got a variable amount. This is a sorry, never mind. You'd have to read into it a bit more, I guess. Sometimes it's not super obvious what the variable amount is and what the fixed amount is, if there is a variable or fixed amount. Like in this case, you've got a thing on per kilometer and a thing on per day, so you'd assume that both of them are actually variable. In this case, though, the implication, well, let's find out. Yeah, so it's the thing that it's telling you to do is think about things purely in terms of kilometers traveled. It doesn't actually say that it has to stay within a given day. But yeah, because the focus has been on writing it in terms of kilometers, you take kilometers as the variable and you take the day as just the fixed thing. So it's $64 for the day with a variable cost of 25 cents. You would use linear. Or you have $89 per day with unlimited travel. So here, still kind of linear because you've still got a fixed cost. It just means that your variable cost doesn't actually exist. So when you do your M for the MX, there's actually no variable, or no letter there, or no number. Yeah, try that again. No number there. So you simply just have y equals 89, horizontal line. Rectangle, find length, rule of area. So we've done this one before, 26. This is maximizing area. This one here, you can see a table, likely to be a piecewise. Initial charge, fixed variable charge, probably going to be linear. This one will actually be a piecewise. You've got a flat fee for a particular domain, and then a variable fee for everything after 20 kilometers. So you'll have I'll even draw this one out actually, just to make it a bit clearer. So if we think about what the axis would look like here, you're going to have cost on the y-axis and then kilometers on the x. Up until 20 kilometers, you have a fixed cost. That's supposed to be perfectly horizontal with a, full circle, yeah. And then a dollar charge for every kilometer after that basically means you have a line with a gradient of 1 for everything afterwards. So that will be described by a piecewise, which they actually give you the framework for, oddly enough, in question 6. Okay. And then, yep, so variable rate for 2 hours, variable rate for the next couple of hours, maxing out at 6. So you have different y values for different domains. This is going to be piecewise, or in this case, different costs for different hours, because you're doing a cost or a fee equation, and it's written in terms of the hours. Different domains, different fees means piecewise. And then this one here is probably going to be area. Yeah, find expression in terms of area. So this is where you have to do a bit of logic to fill out the shape. What I'll do is I'll quickly fill out that shape now, and then we can end that lesson there. Okay, so we have the shape like this. This one was 8, this one was y, this one was x, this one was also x, and these two are left blank. Now, using a bit of logic, you basically have to use the things you already know to fill out the things you don't know. So you've got this full distance here that we're unaware of, but we know that this portion of it is 8, and this portion of it is x. So this portion is now therefore 8 plus x. And then lastly, we don't know this bit, but we know that this full bit is y, and this partial bit is x. So if you take the x away from the y, you get this little bit at the end here, which just looks like y minus x. You now have all the segments of the shape. There's going to be an area equation that you have to do. You either want to cut it off from here or cut it off from here. Up to you how you want to cut that shape up. But once you have the dimensions, it's pretty chill, right? This one has a length of 8 plus x and a width of y minus x. This one has a width of x and a length of 8. So you just do 2 separate area equations, a1 plus a2. That'll get you your area. But that'll have it with x and y, which again is an issue. which is why you then also create a perimeter equation as well, which is just add up the x, the 8, the y, the 8 plus x, the y minus x. You add that all up, and that's going to be equal to perimeter. In part B, you're actually given a particular value for perimeter, which is why that becomes important. Because you remove the p, you just have x and y's in both your equations. You can do the thing we did for the parabola over here to get one variable. All right, that's about it. That'll be the last chapter, 5H, and also there'll be a lot of it in the extended response of chapter 5. Have fun.